In this lecture we are discussing about the definition of complex number. So basically you have learned about the order pair. So that is you have one set, let us say the set is x, then you know that the x cross x is the order pair, the set of order pair xy, where x and y belongs to x. So this is the order pair that you probably have learned in your previous classes. So a complex number z can be defined as an order pair xy of real numbers x and y. So that is z is equal to, I can say it is x comma y. So actually what we are trying to say that it is r square, where it is r cross r, where you can say that this r cross r is the set of all xy such that x and y belongs to r, which are the real numbers. Okay. So not only this, but it is subject to conditions, rules and laws of operations to be specified below. So in that I will say the first rule is the pair x comma 0 is to be identified with the real number x, which is x comma 0 equal to x. I will say this equation is 1. So what we are saying that x comma 0, order pair x comma 0 we identify as a x. This rule actually established the real number as a subset of complex numbers. So generally we cannot say that r square is a r is a subset of r square. We cannot say like this, but we are establishing here one rule that says that the order pair x comma 0 we treated as x, and due to that we can say that the r square is a subset of r square, but in some sense, not in usual sense. Okay, so that is the rule number 1. The second one that I am trying to write here, it is convenient to have a symbol, a name and symbol for the pair 0 comma 1. So it is convenient to have the name and symbol for the pair 0 comma 1, and this pair called an imaginary number. A unit I is denoted as 0 comma 1 equal to I. So this is the notation that we are saying the order pair 0 comma 1 we denoted as I, and we call it as imaginary number. In some of the where they are saying it is I is for iota. Further, if we can say in this, the real number xy are called the real and imaginary components of x and y respectively, and written as real part. So it is r of z equal to x and I of z equal to y. So these are the notation that we are using for the real part x. So that means the order pair x comma 0 and the order pair y. A pair of the type 0 comma y, it is purely imaginary. So it is a purely imaginary number. The third one that we are saying, the two complex numbers are equal if and only if they are real component and imaginary component. are equal. That means if x1 y1 is equal to x2 y2, if and only if x1 is equal to x2 and y1 equal to y2. This is the things we have. In particular, if I can say, in particular since 0 equal to 0 0, z equal to xy equal to 0 0, if and only if x is equal to 0 and y equal to 0, that we can say. The fourth one is about the how to define addition and multiplication over this set of numbers. So if you consider any two complex numbers, z1 equal to x1 y1 and z2 equal to x2 y2, have sum and the product written as z1 plus z2 and z1 into z2, and it is defined as the complex number given by the equations x1 y1 plus x2 y2. I can say this is equal to z1 plus z2, which is equal to x1 plus x2 y1 plus y2, and z1 into z2 will be x1 y1 into x2 y2. So it is x1 x2 minus y1 y2 comma x1 y2 plus y1. So this way this addition and the multiplications are defined. We say this is the equation number 4, this will be 5, this will be, we can say it is 5, and the above one, which is the equality that we have defined, let's say this, and the equation number 2 will be, I will say this is equation 1, I will say this is equation 1, I am changing to this is the equation 2. The equation 3 is about the equality, equation 4 is about the addition, how to define addition, and the equation 5 is how to define. So let us revise what we have done. I am calling this is as equation 1, which is the definition, the order pair. I am calling this is as equation 2, which is says that the component or order pair x comma 0 is denoted as x. I am denoting the equality conditions, that is that two complex numbers are equal if and only if their real components and the imaginary components are equal, and the equation 4 and 5 is defined as the how to define or the definition of the sum and the product in a complex. So if I can sort up, or I can say that if the set R square will be the set of all order pair x comma y, where x and y belongs to R, satisfies the condition 2 to 5, then R square called set of complex numbers. So the elements of this R square which having this conditions 2 to 5 are called the complex numbers, and it is denoted, as you know, it is denoted by C. So I can say the C is the set of complex numbers. So we denoted this C as the set of all complex numbers. So the important things is how the equality is defined, how the addition is defined, and how this product is defined. So that makes the difference between the usual R square and the complex number. So or I can say it is a complex plane when I can draw things over there. So now let us look at going to further. Let's see. Let us consider the order pair x comma 0 plus order pair 0 comma y. So that we can write as x plus 0, 0 plus y. This is by definition of addition that we can say. This we can write as x comma y. Also, if you can see that y comma 0 dot 0 comma 1, that we can write as you use the definition of multiplication, that is y comma y dot 0 minus 0. So I will write y dot 0 minus 0 dot 1 comma y dot 1 plus 0 dot 0. So that will gives you, this will gives you 0 comma 1. So this is due to the definition of product, that is definition of product will gives you this. So if I use the combination of this both this things, that observation, we will write x, the order pair xy as x comma 0 plus 0 comma y. Due to this we can write this. Now let us write x comma 0 as it is, and instead of 0 comma y, due to this we can write down that is as y comma 0 dot 0 comma y. Now this will gives you x comma 0, or rather I can say it is, so that we can write as x plus iy. Why we can write? Because the order, we have already defined a rule, the rule number 2, which says that x comma 0 we can write as a real number x, y comma 0 we can write as a real number y, and there is a notation that we have defined for this order pair 0 comma 1, we call it as imaginary number, which we have denoted as I. So that is x plus iy we can write. So now what we can say is any order pair, any complex number, that is x comma y, we may write as x plus iy. Now what we can have using the same rule, if you have a z which is x plus iy, we may define, so we may have z square which is z dot z. Similarly, we may have by definition of product, we have z square dot z and etc. So we can define all such pairs. Now due to this, what we can say is, what we can do is I square, we know that I square will be 0 comma 1 dot 0 comma 1 by definition of I. We say that it is 0 comma 1. And so by definition of, now again using the product rule, you may check that this will turns out to be minus 1 comma 0, and the order pair minus 1 comma 0 we may write as minus 1. So what we got is here I square will be minus 1. So due to this, if we can write this as I square as minus 1, if we can write I square as minus 1, we may write now, so therefore what we can say is x comma y, which is the nothing but the, so as we have xy now as x plus iy, by definition of addition, that is x1 y1 plus x2 y2, we may have x1 plus x2 plus y1 plus y2, which is similar to write as x1 plus y1. So I can say, which is if and only if we can write x1 plus y1, x2 plus y2, sorry, iy2 as x1 plus x2 plus I y1 plus y2. Similarly, x1 y1 dot x2 y2 we may write as by definition we have x1 y1 minus, sorry, by definition we have x1 x2 minus y1 y2, x1 y2 plus y1 x2. So this is similarly, or which is equivalent to write x1 plus iy1, x2 plus iy2 as x1 x2 minus y1 y2 plus I x1 y2 plus y1 x2. You will have, keep in mind here we have used actually the quantity, that is I square is equal to minus 1. If you do the usual product of these two things, that is x1 x2, then you will have plus iy1 into iy2, that due to that I square, I into I square, that we have here minus 1. So that gives you the quantity x1 x2 minus y1 y2 plus y1 y2. So that is the product that we have. Also one more observation, that is for any z x plus iy, we can have z into 0, which is x plus iy into 0 plus I0. If we use the definition of product, we can have 0 plus I0, which is 0. So what we can observe is any complex number times 0 is 0. So let us conclude what we have discussed in this lecture. We have defined a set R square, which is an order pair. We can call it, this is the same as the set is denoted as C, which is the set of all order pair. We have denoted as this order pair, we have defined as x plus iy, where x and y belongs to R, which satisfies the following rules. The first rule that we can say that it is if you have a two number z1 equal to z2, if and only, so if you can consider the two numbers z1 equal to x1 plus x1 y1 belongs to C and z2 equal to x2 y2 belongs to C, then if z1 equal to z2, which double implies x1 is equal to y1 and x2 equal to y2, z1 plus z2 we define as, so this is the rule number 1. Rule number 1 plus x1 plus x2 plus I y1 plus y, and the rule number 3 we can define as z1 dot z2 equal to x1 x2 minus y1 y2 plus I x1 y2 plus x2 y. So if your the third and fourth rule that obviously that we have is z equal to x plus iy is non-zero if at least one of the number x and y is non-zero. So this defines a complex. So let us give you some exercise here. The exercise 1 that I am giving you is, as you already discussed or already gone through the course of abstract algebra, I am giving you a task is to prove that the following: C plus, as we have defined the addition already above, is a commutative group, and second one, C dot, is commutative group. So these two exercises I am giving you as an homework. After watching this video, you may do this exercise if you have done your abstract algebra course. Thank you very much.